Now we're talking about modeling the fatigue life versus fatigue strength curve. Now at this point, let me quickly comment on whether we should be using the model or whether we need a model at all, or whether data is sufficient. Okay, so we're going to compare data versus model. Now, this is a scenario that we have faced before. We faced this question, or the questions, and expressed the need for a model in the case of the uniaxial tensile test. So in that case, we have data, and the question is, well, can I fit a model to it? Yes, we can fit a model to it, and we have discussed this before. Now, alternatively, we've discussed also the need for a model in the case of yielding. So in that case, for instance, we've drawn the failure surfaces, say assuming that we have plane stress, for a scenario that is perhaps reminiscent of the von Mises criterion. And what we've observed is that there can be data which looks like this, and of course we can put a curve through it which says that the combinations of stresses that lead to failure, principal stresses that lead to failure, form a line that is essentially, in this case, our model. So a similar situation arises, for instance, when we were talking about mixed mode fracture. Well, I understand what happens if there is only one mode, say K1, or only one mode K2, but what happens if I have both of them? Again, you can collect data, and you can certainly fit, again, a model to it. Now, presently, the scenario that we're facing is one that has to do with the question, well, what is the number of cycles to analog scale versus a linear scale for the stress amplitude? What is the number of cycles that leads to failure, or what is the fatigue life versus fatigue strength ratio relation? And again, we can fit a curve to it. So in either case, of course, what we can observe is if the number of points is sufficiently dense and they are nicely distributed, not too much scattered, then I can actually sort of directly make use of the data points, and in all cases, and for a given strain, find the corresponding stress, or determine whether a combination of stresses are going to lead to failure. Or in this case, you give me the number of cycles desired, then I can find the corresponding stress life, stress fatigue strength. But in reality, first of all, there is a lot of scatter in the data, considerable scatter, so it's not very clear which is the best point to take. So for a given life, there will be multiple strengths, close or a little bit far from each other. And two, you won't have that much data points. You will have only a few data points. So it's good to have always a model that can give you a meaningful estimate that is, let's say, the best estimate based on the data available. So that's the purpose of a goal. A model is eventually always useful in qualitatively and quantitatively describing the mechanics of failure, and that's what we are going for. So a model is eventually always useful in precisely, or let's say quantitatively, or at least qualitatively. In other words, it can predict certain trends. So it's useful in qualitatively describing failure mechanics, okay? The onset of failure. All right, so having said that, let us quickly solve an example where we will make use of data and a model. So we're going to look at a AISI steel structure, and if you look at the tables, remember that sigma AR, and in this case it is equivalent, remember, because we're looking at completely reversed loading. So that's equal to sigma A without any stress concentration. So it's going to be equal to the Basque-Quinn relation, which is A NF to the power B, or sigma F prime 2 NF to the power small b, which is the same as capital B. So that's the model, the Basque-Quinn relation that we're going to make use of. So when you look up in the data, you have either sigma F prime and B or A and B provided. In this case, we're going to make use of the form with A. So we have the coefficient as 1643 MPa, and B is a negative value. Now remember that this exponent, capital B equals small b, it's necessarily less than 0 because the slope of this line is always negative. So it has to be less than 0. Okay, so what we are given is that we have a certain operating condition such that the applied stress is equal to 500 MPa. So we're putting a hat because that's the operation life. You don't necessarily want failure under those conditions. So that's what we operate under with a service life, not a fatigue life, a service life of n hat, which is our notation, 2000 cycles. Okay? And the question is, find 1, the safety factor on life, and 2, the safety factor on stress. Okay, so first let's start with part 1, safety factor on life. Now, the way we are going to calculate safety factor on life is, remember, there is a certain number of cycles to failure under the conditions that are provided, but we don't want to cycle up to that point. We cycle up to the service life, which in this case is 2000. So what I need to do is I need to find what NF is. Now, NF corresponds to the life for this given stress. So I'm going to make use of the Basque-Quinn equation, and I'm going to write on the left 500 MPa is equal to A and F to the power B, or to the power minus 0.977. And from this, we would find that NF is equal to little bit more than 100,000 cycles. So therefore, we know what NF is, we know what N hat is 2000, and we can evaluate Xn, which comes out to be 97.1. The ratio of this, 100,000, more than 100,000 to 2,000. So it's a very large quantity, very large safety factor on life. So now we proceed into the safety factor on stress. Now, the way we calculate the safety factor on stress, remember, is there is a certain stress that causes failure, and on the other hand, we do not really want to cycle at that value of the stress. We operate at a smaller value. The operation value is 500 MPa. The value the stress value that would cause failure under our operating condition is the value that will lead to a life of only 2000 cycles. Okay, so in order to find sigma A, we're going to set sigma A equals, again the same equation, NF, which in this case is 2000, to the power minus 0.0977. And from this, one finds that sigma A is equal to 782 MPa. So now we've determined this. Sigma A is 500 MPa, we know that, and we can evaluate XS, and it comes out to be 1.564. Now, look at the safety factors. One is extremely large, one on the other hand is much smaller. So essentially what these numbers are telling us, it's the following. Well, the stress you're applying is 500, and with that, the actual life to failure is more than 100,000, but we're only servicing at 2,000. But if I increase the stress to only 1.5 that value, 1.564 that value, then I'm going to fall back to a life that is much, much less than this by a factor of 97.1 to a value of 2000. So in other words, small changes in the stress, a change from 500 to 782 leads to very, very large changes, decreases in the life from this large value to a value of 2000. And this is not a surprise. This is directly something we observe from the nature of the stress strain curve. So our observation is small changes in stress, we have large changes in life. In particular, if the stress increases a little bit, the life is going to decrease a lot, or if the stress decreases a little bit, the life is going to increase a lot. And that is where modeling becomes very useful. So eventually, you can target a certain life, and if the stresses are not large enough, then you are not small enough, then you can make small changes in the design to decrease the stress a little bit, and that will for sure lead to very significant changes in life. So fatigue is an intricate phenomena, and all of this is eventually governed by ultimately the relation that we observe on a log scale, NF versus sigma A. The type of relation that we observe is this, right? So the reason why there's such a difference in life for a given change in stress is because this is log scale, and the model predicts that change through this power relation, is able to lead to such large changes for small changes in stress. Now let me make one tiny remark here. Our model is always predicting a line, but in practice you might have an ultimate strength. So for this type of material, for instance, because it's steel, the endurance limit is approximately, say, if it's sigma 0.5 times the ultimate strength, the endurance limit is probably going to be of the order of, so in this material the ultimate strength is 1172 MPa, so 1172 MPa, so the endurance limit is going to be somewhere around 586 MPa. So now, although the material might display an endurance limit, what we're doing is we're still predicting life through the blue line. So in other words, for this given stress, we're saying that there's a certain life, and that life is this many cycles, whereas in practice, actually, number of cycles might be very, very large. In fact, you might be able to cycle forever. So therefore, the blue line, notice it's always conservative. Conservative with respect to the presence of an endurance limit. I don't know the data here, it's just a fit, but here it is conservative. So let us highlight that it is conservative in that region. And in particular here, because this value that we're applying, 500 MPa, is below the endurance limit, probably we're going to be able to cycle for much longer. But still, we are presently omitting that and going for a conservative estimate and estimating the safety factor as such. Now, having said all of this, let me quickly summarize some of the current limitations beyond which our following discussions will go. So presently, we've made a number of observations, a number of assumptions that led to the Basque-Quinn relation, which is that relation. Okay? And I understand what it does, and I'm able to do some design and analysis based on that relation, predict between stress, life relation, and if that relation is not satisfactory, I can change my model design and eventually reduce the stresses in design in order to reach target lives, etc. But we have limitations, and those limitations are the following. And there are precisely four important that we're going to focus on. Now, the first of those limitations is that we have assumed the mean stress is equal to 0. But in reality, that's not the case. Structures operate in the presence of mean stress, So the question is, what is the effect of mean stress? That's the first thing that we're going to address, and it's going to be an important discussion. Then what follows is the discussion on the nature of loading. So with respect to the fact that in the experiments and the analysis so far is only based on a normal stress value, there's only one stress component. So in other words, we're looking at a 1D scenario, but in reality you might have multiple stresses. So you can have multi-axial loading, where you have multiple normal stresses and multiple shear stresses, with or without mean. So that's the second thing we have to generalize this relation for. The third relation is we've assumed constant amplitude loading. In other words, we've assumed that the load profile is not changing over time, but it turns out load profiles do change over time. And that's called variable amplitude loading. So we need to be able to address that. And finally, what is very, very important in practice is many designs have notches. We've so far looked at unnotched specimens, and therefore effect of notches is going to be the last thing that we will discuss, and that's going to be also very important. So among these items, 1 and 4 are extensive, 2 and 3 are shorter discussions, but all of them eventually are important to apply fatigue equation, and the basic equation is always going to be the Basquin form. So let's embed that in our minds. I will just write the form based on sigma f prime and coefficient exponent small b, the Basquin relation. We're always going to end up using the Basquin relation, but in a clever fashion to take also these into account. So let's now proceed into those discussions.